Hello. So like what we have discussed in the introductory lecture on grand canonical ensemble, our fundamental aim here is to calculate the quantity known as PRAS, which denotes the probability that our system, which is considered to be a member of the grand canonical ensemble, is found in a state with energy ES and number of particles NR at any given instant of time. So in order to calculate this PRS, we are considering in the first method the equilibrium between a system, means the system that we are considering right now, and a particular type of reservoir known as the particle energy reservoir. So here in the adjoining figure, the system is denoted by as A, and at any particular instant the system is having energy ES and the number of particles of the system is equal to NR, and the boundaries of the system is an open boundary, so it permits the exchange of both energy as well as what? Particles. So both E and N are variable as far as the system is concerned in grand canonical ensemble, and what is shown there as A dash is denoting the state of the reservoir. So what is this reservoir? This is a particle energy reservoir. Okay, so particle and energy reservoir means there are enough number of particles outside the system, okay, which can be exchanged with the system, and there is what? Enough energy outside, and so the energy of the reservoir and the particle number of the reservoir is so high compared to those values, corresponding values of the system at any given instant. Okay, that's the meaning of a reservoir, as we have already discussed. So let's say that while the system is represented by A, let's denote A dash as the reservoir, and if at any given instant, if NR is the number of particles of the system, then at that same moment, okay, NR prime be the number of particles in the reservoir, and ES prime be the energy possessed by the reservoir. Okay, so the the energy exchange and the particle exchange will go on happening until the system and the reservoir attain same value of temperature T and the chemical potential mu. So T and mu are constants. So this is the condition. Means okay, the system is already okay, in equilibrium, thermal equilibrium and chemical equilibrium with what? The surrounding. So the energy exchange can occur like this. So that is the thing. So let the system and reservoirs are denoted in this way. So now remember, ES and NR are the variables here. Okay, both ES and NR can vary with time. Now let's write, or let's represent all these things as mathematical equations. Let's say let NR at any instant plus NR prime, what is that? The total number of particles of the system plus reservoir. Let's denote that one as N0 or N0. So that is a constant. That's a constant. Okay, and similarly, ES plus ES prime, the energy of the system and that of the reservoir, that we can denote as E0. E0 is also what? A constant. So these two conditions will be called as equation number 1. So let's denote that E0 and N0 be the total number and the total energy of the system plus reservoir, right? So this is the condition. And since the reservoir is always large, since the reservoir is large enough, always, that is the concept of reservoir. So we can say that in these expressions, NR by N0, N0 is a total value, NR by N0 is always very much less than 1. Okay, and same manner ES by E0 also will be what? Very much less than 1. Remember these two conditions, which will be handy for us okay, in the coming discussions. Now, what, as I told you in the beginning, what we are interested in is in calculating the probability PRS. So what is probability PRS? The probability that our system A is found in a macro state with NR and ES. So the probability, okay, that the system A is found in a macro state. So corresponding to every macro state, there will be a large number of what? Micro states, you know. Okay. So in a macro state with NR number of particles and ES value of energy, which we have denoted in the figure here. NR ES at any instant t, at any time t, at any time t. And you know, this probability, as per our previous discussion what we had in the case of canonical ensemble system, this probability will be directly proportional to the number of microstates of the reservoir corresponding to its macro state NR star ES star. So for mathematical convenience, we are considering the probability that our system is having energy ES and particle number NR with the corresponding macro state, the corresponding number of number of microstates of the reservoir. The reason was well explained in the previous in the video or lecture for canonical ensemble, because whenever there is a particular microstate with NR and ES for the system, there will be a corresponding microstate for NR. So whether you consider the case of NR ES of the system or NR prime ES prime of the surrounding or the reservoir, you are going to get mathematically the same result. And doing the second one, that of the reservoir, has got mathematical advantages as well. So we are calculating PRS is directly proportional to microstates number of microstates of the reservoir as omega prime n prime, omega prime which is a function of NR prime and ES prime, NR prime and what? ES prime. Which be, there is some technical issues with my writing pen. Let's see. Which is proportional to, once again, omega prime. NR prime can be written using equation number 1 as what? N naught minus NR. So finally it is a function of NR itself. And ES prime can be written as what? E naught minus what? ES. Okay. So there is a functional dependence corresponding to. So let me say that this is my equation number 3. PRS, the P is proportional to. Now what we are going to do, we are having the Taylor expansion, the Taylor series expansion for two variables. The Taylor theorem or the Taylor expansion. Please pardon me for the writing problems. Some software issues. So the Taylor expansion for two variables. Here there are two variables, right? Okay, two variables. Let me first write that the Taylor expansion equation is given by see what you can, f of xy, something like this you can write. F of xy can be expanded about some values a and b. Okay, about the point a and b. So, or you can write f of xy can be just written as f of a plus h comma b plus k. So we are going to expand f of xy about the equilibrium points a and b. So it can be written, it's equal to f of ab. The first term will be f of ab. In the single variable it was f of a plus. F of ab plus, and you know what's the next term? The second term will be what's that? That interval into the first derivative. So here